Good evening.
Yeah, so we can start the meeting as the other members coming. So let me first share this Google Sheet and share my screen. So today, I ask each member who participated in the launch to report what has happened. And the purpose is because we are supposed to submit a brief report, the summary of our launch in Seattle to Kenya Space Agency, because this is a continuation of our relationship. So we have compliance or accountability of our effort. So I'm trying to summarize the what has happened for each rocket. And this is not all. So you are most welcome to add other information. And particularly, so for the recovery group, I didn't follow up what was going on site, especially in terms of a PCB, flight software. So I want to encourage or ask recovery team to put more information because I am not certain were there any damage or circuit for each rocket. Okay, so I think we can then proceed to the presentation. So Samir could summarize this one, the slide, so we can go with it. And I changed one part. So let me reflect that change. All right. Okay, then, yeah, so let me explain my part. Let me go to slideshow. Is it visible?
Yes.
Okay, so this slide is the slides I used for the presentation on Friday. So I already briefed about this report to the next intern group. So they are aware of what we are supposed to do. But let me just do it again. So I summarized some issues which we have found in the launch. Okay, so for the solid rocket motor, for the solid propulsion team, the major issue was the balls. I think Nefat is going to make a presentation later, but he was reporting that the balls which has been replaced just before the launch was silicon bronze. I checked the tensile strengths and it seems to be 275 megapascal. And what we have used for the calculation was a 440 megapascal for the mild steel. And even this is a bronze, meaning the major component of the bronze is copper. So it has lesser melting point, lower melting points, which is around 1,000. So it's most likely the bolts had an issue. So yeah, I think we have to settle this problem. So we need to recalculate and replace it. Next one, it is also solid propulsion. We may not have time to, or we may not need to improve this one for the next rocket. Oh, by the way, I have instructed the new interns, like we are going to launch our next rocket in April. And this rocket is called the N3.5, not the N4, because the specification is all the same as N3, but we are going to improve our design and launch it again in April. So for the N3.5, we may not need to change this one, but port to throat ratio, one of the parameters in the solid rocket motor needs to be reconsidered. Yeah. And then on site, we have observed like there was poor crimping. So they were not able to ignite the igniter first. So they were obliged to replace the igniters. And since their design is not designed as it didn't enable them to replace it easily, so they had struggled a lot. So my suggestion is that we are going to design the igniter maybe much thinner so that it will be reloadable. Like you can remove it and reassemble it on site. Next, yeah, this is what I was talking about. So reloadable igniter. And the plug crimping issue was caused by the inappropriate use of the tools. So you need to use crimping tools, not ordinary plier. And this caused the loose connection. So and also we need to measure the conductivity once you develop the igniter, because if we did it, we were able to know this igniter didn't work at the laboratory. So always we have to measure the conductivity of the igniter. So this is a kind of a quality control issue. For the airframe, apparently our rocket body tube didn't have sufficient strength, especially where we are fastening our solid rocket motor. We had a lot of rip, so it doesn't sustain withstand against the thrust generated by the SRM. So the method we tighten the SRM to the rocket body needs to be reconsidered and redesigned. Then the recovery system, the state didn't change. So I think Ian is going to report what the reason of why it didn't change the state. And the parachute ejection was unsuccessful because basically the rocket didn't go as expected. So our expected launch is about 1.6 kilometers. However, because of the SRM explosion, I think it just went up to 100, let's say 100. So recovery team made us kind of they had a mechanism that they are going to ignore the altitude less than 100 meters, meaning they are not supposed to eject the parachute in the altitude less than 100 meters, because this is a kind of safety measure, like to avoid the accidental fire of the parachute. There was such a threshold, but our apogee didn't reach such a threshold. So we are not able to confirm the successful parachute ejection. Yeah. So in the next test, we are going to test it. Ejection delay. So in the testing in JQuat, we observed it normally involves a few seconds delay, like 2 to 3 seconds. So the next recovery team needs to reduce such a ejection delay. So ideally, it should be 0. But I think they already started how to improve it. I think they had a presentation on it on Friday. So they will test it. Regarding the airframe, there was a launch pad issue. And actually, this the major issue was actually solved on site. So initially, our design is to fasten our launch lug onto the rocket. So they use the epoxy to adhere it. However, we found out we shouldn't adhere the launch lug to the rocket to enable the smooth ejection. So that was one observation. And also the deflector plate, we are still discussing it, but we may need to redesign the deflector plate. By the way, the deflector plate was damaged heavily, so we have to refabricate, even if we are going to use the same design. As for the recovery, we need to fabricate a PCB much earlier, because on the last dry run, we found out the PCB doesn't go into the rocket. So avionics bay was too much bigger. So we should avoid such a last minute work. Then there was also an inversion of the JST connector, ground and 5-volt. It was mixed up. So because of this, the 2 Raspberry Pi Zeros was broken. And also, because of the last minute PCB design change, the buck converter was also replaced to another type, and it generated another issue, right? Like this buck converter cannot have capacity to source 3 components, ESP32, GPS, and Raspberry Pi. So again, the last minute work it should be avoided because we don't have much time to test it. Telemetry, for the Tembo, the first rocket we launched, initially it was working, so we were able to receive the signal at the base station. However, especially for the first rocket, we took much time after we assembled the rocket, like 1 hour. So during this preparation period, the signal was lost at some point. So we need to identify this reason. I think recovery team may also can report. And this is my suggestion for the recovery team. Because of this longer idling time after you settle recovery system in the rocket, we need to have more work, like assembly of the airplane, assembly or hanging the rocket onto the rail, and ignition circuit preparation. So there will be some idling or waiting time, more than 30 minutes. So we want to avoid the accidental rejection of the parachute, let's say, for example, because we have seen it in the Tembo rocket, the first rocket, we have accidentally fired the parachute and we lost the crimson powder. So to avoid such accidental rejection, I suggest that we are going to equip some mechanism like arm, disarm kind of system, or engage, disengaged. So I mean, this can be triggered remotely. So after we settle everything, after we prepare the rocket onto the rail, we are going to arm it so that the parachute will be able to eject at any time. The next one also suggestion from myself. So because we have observed there is a risk of mis-ejection of the parachute. So, and I think this is a kind of risk for everyone who is working around the rocket. So once the ejection pin is turned high, I suggest that we are going to beep the sound, like using a buzzer. So when the ejection signal is on, we also need to beep the buzzer. So this is just a safety kind of measure. And then as for the recovery, ejection bolts short circuit, we have seen a lot of problems. And actually, I heard it was kind of based on the Pro design. So the MOSFET gate pin was too close to 12 volt. And also the soldering was poor. So, this issue happened. So for the next ejection PCB, I think it should be redesigned so that you can get much better design, and also to avoid this short circuit. And again, the last minute, because of the last minute work, we didn't have much time to confirm there is no short circuit. So again, we have to prepare in advance. And also as for the crimson powder, because I say there was accidental firing, so we lost 10 gram crimson powder. And I noticed that recovery team only carried 48 gram of ejection powder, crimson powder. And since we are supposed to launch 4 rockets, and each rocket consumes 10 gram, ideally we can just use 40 gram, right? But they carried 48 gram. So if they lost 10 gram, meaning there is one spare, like 8 gram backup. But apparently 8 gram backup is not enough because they know 10 gram works and not 8 gram. So considering such accidental cases, we have to carry the backup, like more than double. So in that case, if we are going to use 40 gram for the launch, we have to carry more than 80 gram, a double of 40. So I think we needed to carry, let's say 100 gram in the last launch. Back to the solid propulsion, the remote ignition circuit had an issue, especially for the last rocket, Kifaru. So for the first rocket, the remote ignition system was working, but at the last rocket, it was not working. So they suspect the issue was due to the low battery voltage from the power bank. So if we had carried the power bank as a backup, they were able to launch it. So also we have to carry the power bank, more power banks as backup. Then this was raised by our members. So, when they went to Isiolo, most of the work was done by a few members and others are kind of relaxing, or maybe they didn't know or they couldn't contribute because they were not so much involved or, yeah. So this is a kind of a knowledge sharing issue. So we have to make a documentation and also maybe in the dry run or maybe the preparation on the lab, we have to, so everyone has to practice how they can prepare the rocket. And also the knowledge sharing, I think Ian will raise this issue. So we have to run from the current asset, like N2, etc. Yeah, because there is a lot of duplication. And also, what has been done is actually it is not so much reflected on our current system. Then back to airframe. So we have to make sure if all the bolting are done. So this was also raised by one of our members. So yeah, I think that this is raised by Mohammed. So maybe Mohammed can comment more. And also this is also my suggestion. And also Madime and Jeremiah from Airframe mentioned it on site. So instead of making our rocket body using a glass fiber and aluminum, by lowering it, by applying the resin, why not finding a prefabricated material? Prefabricated material means it can be a aluminum cylinder, it can be a fiberglass cylinder, which we can obtain locally. So it may be okay to post-process a little bit, but if we can use such prefabricated material as it is, it will help us a lot. Or even outsourcing is another issue. We can also consider it, if not too expensive. So apparently we have an issue for fabricating because our cross-section of a rocket body is not a true circle. It is a kind of oval that prohibits to avionics bay to be inserted. So rocket body must have a precision so that we avoid the back and forth when assembling our rocket. Good. So I think I hand over to Ian. So can you proceed to the presentation?
Good evening, everyone. So I'll share my observations from the N2, N3, and N3 rocket launch that we did in Isiolo. So some of the observations from the first rocket, we can, during the initialization of the first and the loading, when the airframe team were loading the avionics bay into the rocket, the transmission of the data was successful, and you could see like correct, relatively accurate sensor data was being transmitted to the base station. But when the first rocket was moved to the base station and put on the launch pad, after a while, data transmission to the base station was unsuccessful. I think the reason would be the antenna, the way it was placed. Since for the second rocket, when we removed the antenna from the mounting rod, we were able to like continuously get data from the rocket. Also, apogee detection was not successful, and ejection was not successful due to apogee detection not being successful due to the threshold Dr. Oki mentioned before of 100 meters, since we expected the rocket will go to around 1.6 kilometers. Yeah, next page. For the second rocket, it's same case. Initialization and loading of the rocket, data transmission and reading was successful. Also, like I said, when the rocket was moved, after we moved the antenna towards closer to the rocket and we removed it from the rod, and it was being held by someone, the data transmission was also continuous, so the data transmission worked. Also, data logging and flash memory was successful. Based on the recovered ESP32, we were able to get data from that. However, apogee detection and ejection was not successful due to variations of the data that we received. This will be pointed out later on. I'll continue. Yeah, as you can see, the sensor data collected and transmitted do not represent the actual readings that we expected from the launch site. Since, for example, this is readings from when the rocket was on the launch lag when they were fixing the issue with the launch lag. You can see it's reading altitude of 875 meters, while basically most the altitude in Isiolo is around 1276 meters, if I'm not wrong. So if you put into consideration these variations, you will not the sensor data will not work with the same machine, since the base altitude is calculated when the rocket when the PCB circuit is turned on. We calculate the base altitude, and when it was turned on, the readings were accurate. It was representing around 1300 meters. So all these values that came after, even during the flight, they will be below 1300 meters. Hence, it will never detect that the rocket has launched. Next slide. For the fourth rocket, data readings were not checked, and however, Wi-Fi connection was successful, and we anticipated to use the Wi-Fi connection through MQTT connection to carry out manual ejection. The manual override code was initialized and found to be working okay. However, we were not able to carry out our testing since this was not possible as it was late and the code was designed on site. Also, the PCB circuit had some issues and had to be altered on site, which was also another issue. And however, the rocket was never launched due to time problems. Next slide. So some of the recommendations, we will need to come up with a better antenna mount based on the first rocket, since data was not being transmitted when the antenna was mounted on top of the current antenna mount. I would suggest to create a mobile antenna mount that can be moved to follow the rocket trajectory during the flight and even on the base station. We also need to design a better state machine and come up with better apogee detection algorithms and launch detection logics. For example, the 100 meters threshold, you see, it didn't work correctly. And also, we have some issues with our apogee detection algorithm. We also need to determine our PCB design thresholds by carrying out enough tests and stress tests on our PCBs under multiple conditions to simulate the actual environmental and human error factors that happen during launch. Since most of our designs and testing are usually under ideal conditions where your PCB is just placed inside a room where the temperature is ideal, there are no movements, there are no vibrations. So when you do the testing, it will obviously show you the correct values. But if you based on the experience you've had during launch, these conditions are barely what you expect, for example. Also, we need to incorporate fail-safe contingency plans for the rocket. For example, premature ejection fail-safe, as explained before, where the first rocket ejected prematurely. You also need to create a better manual ejection mechanism and time ejection in case apogee detection fails. Next slide. We also need to implement a better PCB design way beforehand and be able to test it out. This is based on the issues and the errors encountered during the launch that we had, where we had to fix the PCBs on site. This needs to be fixed. It's not a good plan. Also, the knowledge sharing. We need to generate better docs that can be used by future teams, and this will result in less time taken to redoing tasks. We noticed that most of the tasks that were being done by N3 had already been done by people in N2. For example, PCB redesign, coming up with the N3 flight software. All these things had to be done, and yet we had stable systems that had already been designed before, and they were working. Now the time used to redo all these things will be better used to improving them, or also coming up with newer or better ideas. We also need to implement over-the-air updates so that in case once the PCB has been loaded into the airframe, we don't have to remove it. We can be able to adjust code if we need to through over-the-air updates. And for the suggestion of arm and disarm mode, I would suggest you implement deep sleep for the flight computer, and only fully turn it on when we are like when the final horn has been when you hear the final horn, and when you're close to launch, that's when you can remotely turn the PCB on from deep sleep. This can be done. Also, we need to fix the lag in the base station. It currently does not show near real-time data that it receives from the flight computer. This beats the logic of being able to see real-time data on the base station, since we notice there's a very long delays from the data received and the data shown on the client side. There's a lot of lag between the server and the client. Yeah, I think that's it.
Okay, thank you very much, Ian. So proceed, Samir.
Yes, thank you. From my end, the observations I had, firstly, we'll start with the solid team, that is the PCB casing. We had thought that we will have a full enclosed PCB, but on site we found that we were covering the PCB with a metal sheet. That worked, but it was still not foolproof. In case there was some fire or something, the batteries would have been burnt and damaged the PCB. The second problem we saw, or I saw, was that ignition delay. From the word ignition, there was some delay, so that may lead to some safety issues, as we don't know what is happening, and that also wastes time, as we cannot go near the rocket. The third has already been pointed out by Dr. Aoki. For Simba, that is the last rocket, the ignition failed. So the solutions I suggest is ensure a proper casing is made for the PCB. We were using helmet PPE, but helmet is a PPE for personal protective equipment, not casing. So I suggest that we come up with a better design and a better form of casing. The solution to ignitions is have spare igniters and modular circuits. Modular meaning, if I'm not wrong, the ignition team or the propulsion team had one circuit ready. That is, we were using one circuit for all 4 rockets. So for future launches, I would suggest have spare igniters and circuits, such that if any one of them has a problem, you can simply plug out and plug in a new one, especially ESP32s. And for Simba, I would have suggested that we can test and prepare the circuit before countdown, so that when the team is when the recovery team or the airframe team is working on the airframe, the solids team can work on the igniters. Next slide, please. For airframe, this was pointed out by Major Were, that we had both of the rockets. The first 2 rockets had fiberglass airframe with aluminum solid motor, and the last 2 rockets were aluminum airframe with mild steel SRM. So what happened is that what the point was that if we don't have a different variable, we cannot expect different results, such that once we've launched our first rocket, we already saw, as pointed out by Dr. Aoki, that there was that, as you can see, the shear by the bolt. So the second rocket we were about to launch, but we realized that we will not expect any different results, because the second rocket was also fiberglass with aluminum SRM. So just for different results, we can try interchanging them. Next slide, please. For recovery, on the base station, we had the serial preparation of the flight computer, which caused some lag and delay, because we had to wait for each rocket to be done, retrieve the PCB, and move on to the next. So that was some of our issue. And then on general, we had a we can use mechanical tag and lockout. That means that we can use, I've seen some guys, especially NASA student rockets, use screws to switch on the airframe or the entire assembly. So what they did is that instead of assembling everything on site, they have everything assembled and ready. And when they go to site, they use a screw which is used as a mechanical switch, and they turn on the screw to turn on the entire system. So that means that the airframe was, or the entire rocket was prepared beforehand and delivered to site. And just another suggestion would be use a rocket carrier to avoid braking during transport. So we noticed that one of the fins of Simba was damaged due to transport. So we can come up with a carrier. That will be just a wooden case or something, just to ensure that we don't have anything breaking. And we can use spare ESP32s, especially for the recovery team, to help us in case that one ESP burns out, which is which can occur very easily. So we can just replace the ESP32 instead of borrowing from another rocket. I suggest that we have a spare, okay, we have a network engineer, so that we can have parallel preparations of the rockets. What we noticed is that we cannot prepare all the rockets at the same time, because we cannot, we had to ensure that only one rocket is communicating with the base station. So we need a network engineer to come up with a way that we can connect multiple rockets with maybe different base stations at the same time using the same network. Yeah, next slide, please. So in general, we had the photos and videos. We were able to get a copy of the photos and videos from the KSA personnel, but unfortunately, the partition that was that had the backup got deleted. So far we don't have the photos and videos of the launch, but I am communicating with the Dennis to upload them and share them with us. The photos and videos were copied to our laptop, which the partition got deleted too. Yeah, thank you.
Thank you very much. Well, yeah, thank you very much. I also wanted to add about this shooting. So, oh, this is not just a moment. No, camera. Okay, so I uploaded all of my shooting, the videos. There are 4, and it is listed on this Excel sheet. Like a video which has been taken by GoPro, a Canon camera, a Nikon camera, and my smartphone. So these are the links. So if you want to see the actual flight, you can watch it. And also I realized that I made also mistake or maybe improvement, because this is kind of, I'm against the sun. So this is not so clear. Initially, it was okay because of the position of the sun was just behind. But after passing the 3 p.m., 4 p.m., it just shifted to this side. So I didn't realize it. It was an issue. So, but anyway, this is another improvement. And also, yes, so I'm willing to receive the videos from KSA. So we are going to continuously push so that they can send it or share it. Okay, and also I have one more slide from NEFAT. So could you proceed?
Yes, good evening.
Good evening.
First page is basically a summary of how every rocket did. For Tembo, we had the nozzle ejected, the bulkhead, and the bolts were cut. For Kabura, we detected a loose connection at the connectors after a failure to launch. We had to remove the igniter and test the neutron wire, which is okay. We used the backup igniter, but the igniter was placed at the nozzle's end, which wasn't okay. The result, the nozzle was ejected, the bolts were cut. For Kifaru, the bulkhead was ejected, the bolts were cut, and we had damage to the airframe. The nozzle was intact, but the bolts attaching the rocket motor to the airframe were cut. And we also observed some fuel which had not burned. For Simba, we had ignition circuit failure, which upon testing, we realized we had a problem with the power bank. And maybe we can go to the next slide. Yes, we've outlined some of the problems we noticed. The ignition circuit was hanging there. We'll have to use longer wires, maybe modify the ignition circuit and the electronics casing, and ensure everything fits and is well covered. And for the bolts, later I've explained why the bolts ended up that way, but we can see the results of the bolts. Once the bolts failed, the rocket really couldn't fly anywhere. We can go to the next slide. Here we can see the loose connectors that we are talking about. We had used the pliers to clip, but seems it wasn't enough, and we'll have to check on a crimping tool. And we also had to think about modifying our igniters so that we can have a way to replace the igniters in case one fails, and we are already on site. Next slide. As we can see on Kifaru, here is where we noticed the fuel that had not completely burned. This means that our grain preparation and our storage mechanisms still wanting, and we'll have to improve on that so that we can ensure that the fuel is okay. The bulkhead was ejected. As you can see on the bottom left corner, it really damaged the airframe. Next slide. For Simba, we were not able to launch, one because of the power bank and also because of time. Next slide. So yes, we did some research on the bolts that we had bought, and we realized that they were silicon bronze, and they were not really adequate, strong enough to hold our motor together. We need steel bolts, and we'll have to buy some and do some testing so that we can confirm that the bolts are no longer an issue. Next slide. Yes, for the ignition circuit, we'll have to really modify our ignition circuit, and we'll have to also, we only had 2 ignition circuits and 1 extra igniter. We'll have to make at least an ignition circuit for every rocket so that we can have the parallel setting up and avoid any delays, and also have backup plans in case one fails. And we'll also look into how we can modify the igniters. And maybe our last page on the recommendations. Yes, we'll have to recalculate the number of bolts required and make sure we use steel bolts. And we were not able to conduct static tests before launch. Maybe that would have shown us the weakness of the bolts. And we'll have to do more static tests. We also have to ensure we have extra power banks and have appropriate tools, and also continuously test our circuits and our igniters. We have to improve on our grain preparation techniques and storage. This means we'll have to document properly on our grain preparation techniques. And we had a desiccant, but it appears that we were not really able to store them well still. Some got damaged, so we'll check on that. We'll improve the design of the electronics casing. And we will also improve the design, the ignition circuit. And we will also consider the development of a reloadable igniter. That's all.
Yeah, thank you very much, Nepat. Airframe team, do you have anything to present? Or even if you don't have presentation, you can just speak up. Marime or Jeremiah?
Hello, good evening.
Good evening.
Okay, I'm sorry I didn't make presentation slides, but I did write some things down. I think I'll just go through them and then maybe send the slides a little bit later.
Okay.
All right. So for us, these are my personal. We didn't get to discuss as a team, but these are my personal observation, and I believe most of my team members will agree with me. So I'll start with maybe the launchpad. So generally, I think the launchpad did well considering everything. Apart from maybe the minor damage it received after the first launch due to the lag being stuck, but it stood and there was no visible damage to the structure of the launchpad and everything around it, apart from the blast deflector now. So during the first launch, we had a lag stuck. The upper lag of the rocket was stuck on the launch rail, and therefore there was a little bit damage on the rail and we could not use it. We had now to turn it over and use a good side of the rail to continue with the other launches. And then, like I said, the deflector plate was also damaged. It was hit the first time with the nozzle that had been ejected, and then I think the second time with now the complete assembly of the SRM, which damaged it completely on one side. But it was not damaged in any way by the thrust. The exhaust fume, those exhaust gases of the rocket. So I'm assuming that was good on its end. The material was selected properly, and there's no damage due to the exhaust flames. It was just that there's that physical impact by the nozzle and the SRM, and therefore we had damage. So at the site, Captain Were pointed out that there might be hints of twisting moments on the launchpad base. He pointed out that two legs of the pad were showing some motion on the base, and on the pegs they were a little bit displaced, while two seemed to be intact. So he pointed out that may be a result of some twisting moment, and he was saying that maybe that may be caused by now our thrust not being perpendicular to the rail, or now the blast deflector affecting the direction of the rocket, such that now with the blast deflector it's causing a reaction on the rocket such that the rocket is coming out at an angle, hence causing that twisting moment on the base of the launch pad. So I'm not very sure on that, but I think that is up to investigation. But as per my own opinion, I think the base was okay, the blast deflector plate was okay. It was maybe just a little bit motion due to the rail, maybe now an issue of offset thrust, that is the motor may not have been perpendicular to the airframe, and maybe some of the thrust may be deflected to the side, and therefore maybe the rockets are not coming at 90 degrees, maybe they're coming at a given angle, and hence causing that moment on the base. So for our launch pad, I think, like you pointed out, we may need to rethink the design of the blast deflector so that we offset any issues that maybe in the case that Captain Were was right, and we have an issue with the reaction from the base from the deflector, then maybe if we redesign the blast deflector, that problem will be gone away. And also maybe with another redesign of the blast deflector, we'll have a better product for future launches. And then another thing from there is now to check the rail to ensure that it is straight, and to ensure that once the rocket is placed on the rail, that there are no loading. For example, for the first one, it was the upper rail was stuck because the weight of the rocket was pulling on the lug, and therefore it got stuck on the rail. So maybe next time you can check on the loading of the rail so that there's a smooth movement and nothing is pulling on the other. Apart from that, I think I'm done with the launch pad. I'll have to move on to the first airframe. What I noted. So, like many people have said, for the first airframe, the nozzle was ejected and we lost power, and therefore the rocket did not go very far, and the bolts were observed to be sheared completely. So, what we noted from the airframe team was that the first airframe that was launched, it was an aluminium one, and the bolts that were used to mount the SRM to the airframe, there was some shearing on the skin of the airframe for quite a considerable distance, which was worrying. And that brings up either now our airframe was too weak for the motors, or now the motor was too powerful for airframe, which is basically the same thing. But it was worrying for me because logically speaking, the motor and the airframe are going in the same direction, so there shouldn't be that much damage. The only reason maybe for that amount of damage due to the shear we saw on the skin would have been if there was resistance on the rocket from the top, which was quite a concern after the first launch because we had the lug being stuck and it could not move. So we thought that the resistance of the lug is what had caused the motor to now try and push into the rocket, and that's what caused the tear on the skin of the airframe. But then after the second launch, in which the lugs were perfectly ejected, we still had the same amount of damage, that is the tear on the skin, and therefore now it's an issue of probably now our airframe was too weak. Maybe we should consider reinforcing it, or maybe increasing the number of bolts. But I think even if we had 8 bolts, there still would be some shear on the airframe because that damage was too huge. Like the shear was too much. If it was just ovulation or maybe a small tear, then it would have been okay. But the tear on the airframe the distance that the bolts had moved inside the airframe was too much. So I'm thinking it's an issue of the airframe was weak for the given motor. And then apart from that, the rest of the damage on the rocket after the launch seemed to be due to the fall and not having recovery working. So I guess everything from that is in order. So what I thought is that we as a temporary fix, we decided that for the next launch we will not fix the lag. That was suggested by Captain Were, so that now we do not have an issue of the lag getting stuck. He said that we should do that because in the case that maybe there's a little bit of resistance, then instead of the lag being stuck and having damage to a rail or the airframe, then the lags will just burst and then the airframe will continue on its way. So that's what we did for the 2 other subsequent launches after the first one. But then we found that after that, all the rails were smooth. It was only, I think, it's only the last launch that left a single lag, but all the others went away with the lags. So as a proposal, we need to ensure that the airframe is stiff and strong enough to avoid any tear on the skin due to shear of the mounting bolts or screws. And then we need to ensure that the lug is placed such a way that it slides smoothly out of the rail. Like I'd said, instead of having the weight of the rocket pulling on the lug, it should be placed such a way that it moves smoothly and that the weight is perfectly balanced. Okay, so onto the second airframe, which was also aluminium, so it's similar to the first. So for this one, the only thing we had changed now is that we had not permanently fixed the lugs to the airframe using epoxy glue. So, but then the results were similar. We thought that not doing that would at least save the nozzle from being ejected, but then the nozzle was still ejected and we still had the bolts on the nozzle being sheared, and we still had a similar amount of damage on our airframe skin as compared to the first one. So from that, the rest of the damage was mainly due to the fall because we had no recovery. So for that now, we could not propose much, because now our theory of the problem being the lag, or the problem being the resistance of the rail was thrown away, sorry. And so we now had to think, we now had to go with Dr. Oki's proposal or hypothesis that it's the motor that's now, there's too much pressure in the motor, and that's causing explosion and ejection of the nozzle. So a suggestion that was made on the field during our launches was that now we should consider a way of maybe having a redundancy, such that even if the bolts on the nozzle shear, we still have a way of having the nozzle rigidly fixed to the airframe, such that yes, the bolts holding the nozzle have sheared and they've failed, but then the nozzle is still goes with the airframe, and maybe we can have a little bit more distance in the rocket. So a suggestion was that having some 2 bolts below the nozzle, and then they're rigidly holding the nozzle in place, maybe 2 or 4, maybe 6, such that even if the bolts holding the nozzle to the casing or the airframe fail, we still have something retaining the nozzle within the airframe. Maybe that can be checked out for the future. The third airframe was our only fiberglass launch, the CFRP. So for that one, now it was different from the two airframe rockets, because for the aluminum rockets, we had a case of the nozzle being ejected, but for the carbon fiber, now the nozzle was in place intact, but then now the bulkhead was now ejected in this case, and that caused an explosion at the joint between the motor section and the avionics bay, and that just burst the entire airframe, the airframe at that point, and we had pieces being thrown off. And I think it was with that we had incompletely burned grains being thrown away. And what was even more worrying was that explosion took place. I think it took place in when the rocket had not yet gone off the rails yet. So for that, I'm not sure much about it, because it's different to the other two, but it's in a way it's similar, because it's still a case of probably having too much pressure in the casing. But for the fiberglass, I think fiberglass is brittle, and hence the rupture at the point of explosion. And then for this one, there were no tears or scratches, just the exploded part at the joint between the motor section and the avionics bay section. So like I said, the casing and the nozzle were intact, but then they were ejected, just as was the case with the bulkhead, and the casing and the nozzle is what hit our deflector plate and ruined it. So I think, like I said, let me check my notes. Exploded. So for this one, no, I did not pick up much, because at this point I think there was sort of like a pattern to the launches. The launch starts well, and then there's an explosion. So for that, I think maybe we need to rethink the material, because maybe if it was aluminum, we'll just have a dent or maybe a single tear, but then because it was fiberglass and it's a little bit brittle, then it's just some pieces of fiberglass being thrown away, and it could not hold past that. The airframe, I think, broke into 2. So overall, I think the only positive we had as the airframe team was that the rail did fairly well. And then, as I think Captain Were pointed out, the rockets were launching straight. So maybe that's a little bit congratulations on the people who designed the fins, because shows that the rockets were stable off the road. And maybe if they'd gotten the chance to go far, maybe we will have received some positive results. They will not have come tumbling down. So apart from that, the only concerns we had now were the shears on the screen of the airframe, which meant that we now have to either rethink the connection of the SRM to the airframe, or now considering now strengthening the airframe, on which there are 2 options. We can use a stronger material for the airframe, or we can have maybe like an exoskeleton, and then have the covering of the airframe just as a way of aesthetics and covering off, but the main the main strength is being provided by the exoskeleton inside. And then, like with many teams, they also had a problem with the last minute modifications. For example, for the fourth rocket that was not launched, we had to redrill because there's an issue with fitment, and we had to redrill the holes for the coupler. And because of the rush being the time running out and everything, I broke a drill bit, and we had to now rethink and use larger screws, which took even more time. So I think for us, we also have to avoid last minute changes. I think that's all I have for now. Thank you.
Okay, Martin, thank you very much. Now, we have 26 participants in this forum. So if anybody wants to make any comments, you are most welcome. Is anybody willing to contribute?
Good evening, Dr. Oki.
Yes, good evening, Captain Were.
Good evening, team. Generally, first, I would like to express our sincere gratitude on behalf of Kenya Space Agency. The team did really good. You could not progress from the previous activity. There was improved coordination, and the way the activity was undertaken, actually, critical factors about launch and rocket handling were observed. First of all, in regards to timings, you could see the coordination of that is Samil and the team, the AIM's team, the ignition, the ignition sequencing and all that were all done as per the safety standards that we expected. Okay, about the outcome, maybe rocket number one, if you could replay the video, you could see that the liftoff was clearly vertical. There was an evidence of good stability of the rocket because it was very stable as it lifted off. However, the only thing that maybe led to what we attained could be there was some sort of either friction or restraining force, which you could see by evidence of the shearing. And if you look at the shearing direction, it's like it's not in the opposite direction. Like the direction of shearing was sort of the rocket is trying to move upwards, but there's a restraining frictional force that is dragging it behind. So when we looked at the only thing that we could not do to coordinate with the recovery team was before we could take up our fragments, we could have taken the photos of the scene. I think that's a failure on our part. We did not allow time to take the scene photos and all that to use that to do the reconstruction analysis. So my take was the restraining forces, as you said, it's like the lags were, because the first one we had mounted the lags and we had fixed the lag on the airframe with the epoxy. So the rocket was integral to the lags, and the lags were not freely moving in the rail. And you find that at the exit point, there was a nick that developed, which means that there was like a twisting moment at that point. And it was a single point of failure, which suggests that the forces, the twisting moment at that point was so intense that it could bend the rail. So that suggests that two things. One, the frictions were extreme, but we rule out that because the surfaces had been greased well. Two, the fact that the motor could eject out of the airframe at that point also suggests that maybe the reaction force was was highly restrained, because if we say, for example, the chambers were at high pressure, the likelihood will be that there would be an explosion, and more so on the rear side of the nozzle, because we expect that if the back pressure is the driving factor, when the pressures are not balanced, it means that the diffusion and the convergent divergent nozzle are not effective. But you could see that there was no evidence of destruction if you looked at the motor itself, like the nozzle part. There was little evidence of destruction, which means that suspiciously the destruction was arising from other factors. One, looking at the rail, because it bent because of an external force, it means that these are factors related to the dynamics of the rocket as it was lifting off. And also, looking at the direction of ejection of the motor, because we noted that it hit first the deflection plate, then rolled, hit the ground, and you could see that it rolled like the first point of impact was tangential to the deflection plate. You could see that this was something that was struggling to pull another part, but it is facing a lot of resistance. So likely is an element of one, there is an element of if you look at how we were jointing the parts, like the way we were bolting, you find some of the bolts were highly protruding on the surface. So there is an element of interference, like the airframe body was not smoothly smooth and free to move about. So there is a likelihood of interference due to protruding nuts that could even stuck on another part of the launch system. Equally, the placement of the bolts, if you look at the tearing, you see it was just longitudinal. One bolt takes a day. I wish the next time we do it, we try to balance the points of failure rather than giving it a direction tear. It might have it like we arrange the bolts in a manner that they could not amplify the stresses. They rather reduce the stresses. So in the way we design the positions of locating the bolts should also be an element. Then I'll push for smoother bolts, smoother surfaces, so that we eliminate any chances of interference in case of during liftoff. Equally, I still insist that we investigate on the element of the deflection plate. It is a good idea. In fact, it enhanced our safety because it gave the rocket, the launch site, a bearing of the safety side, because the best approach side was opposite the deflection plate. You knew that when you come from that direction, there's no chance that in case of failure, you'll be hit by any component of the rocket, because most of them were being diverged to the direction of the deflection plate. But the location, we still retain it, but the location, we give it some sort of clearance so that we eliminate chances of the flow interruption due to an obstruction. Because if you look maybe in the general principle, if you looked at the design of a Harrier jump jet, you will see that whenever you turn the nozzle, you give it an angle turn, the thrust of the aircraft also could respond in that manner. So you turn it down, the aircraft attains a vertical lift. You give it a horizontal push so that it is lateral, it is in parallel direction to the airframe direction. You realize that the thrust becomes parallel. So the location of that deflector plate and the distance between where the nozzle is and that difference might also contribute to what you are seeing as the twisting moment at the on the rail, and equally the rising pressure inside the combustion, that's the motor. The reason is that you are creating a high pressure environment internally, and which is normal, because you have to create internal pressure to be high, then you diffuse the pressure to atmospheric pressure uniformly, so that in compensation we generate thrust. However, now you are putting a surface close to the nozzle, so the higher pressure inside, and instead of diffusing, instead it creates a pocket of an external pocket of higher pressure due to the compressibility effect of the proximity of that deflection plate to the nozzle. So you find that the whole thing amplifies and affects the normal flow from the rocket. So the likelihood is that, one, it will deflect the thrust arm of the flight of the rocket. Two, the micro pocket of the high pressure will affect the burning characteristics of the fuel, and that will create a situation whereby the water cannot balance the pressure. So the likelihood is that it will explode, whatever you are witnessing. So you find that the two likely scenarios have been computed because of the proximity of the nozzle ejection to the plate, due to those reasons. Then equally, in terms of creating the design of the bulkhead, I saw you are putting a bulkhead as a component. I'll prefer that the next airframe design, we put it as a module whereby the whole system be completely sealed, so that the next level, like the next compartment, just have an attachment to this, but they should not have a free attachment in form of a bulkhead. The bulkhead should be an integral part of the lower casing, so that we eliminate those chances of a bulkhead contributing to the failure. Then also I observed that the antenna, the base station, the way it was, though we say that it was omnidirection, but there's chances that it lost a line of sight, because you could see that at certain height we could not communicate. Because maybe as one of the team members suggested that we could have a mobile base station, which could allow for pointing on the flight path, so that we at any point we maintain contact to the flying rocket. Then additionally to the failures we witnessed on ignition system and all that, I may recommend that we design the system with a redundant mode, which shall allow for maybe a primary and a secondary circuit, which shall allow for just a quick changeover in case of failure of one of the lines. Furthermore, I recommend that in the course of design of, the switching off the arming of the rocket be done, maybe if we could give it, if it is not done electronically, then we give it a sufficient an access window that will facilitate that, because we could not just turn it on, turn it off until we disintegrate everything. So if we could, in the airframe, we could provide for an access window that can allow for manual override of the same, that will be an improvement on the design. Otherwise, the team, we are hopeful that this was a better step forward. And going with the results, I think from our side, we will we look forward to improving on being present in the progress, so that we don't come on the last day, so that we can have also enough and sufficient time to test the systems in situ before they are integrated to final launch. So I'll be organizing my team so that we have dedicated time with their team so that on and off we can reevaluate the designs. And we were proposing for the plan, a comprehensive plan that will show the event, so that even if we seek the clearance and approval for the range, we know that this interval will be doing, maybe we don't need to do 4. We can only go and do 1. But as long as we've improved and it's performing better, that will be a better step than waiting for the 4 for us to do one day activity. So I'm looking forward for that program to come out, and I'm looking forward for enhanced engagement with our KSA team, so that we can monitor and we can participate in the project. And kudos for the alumni who made it to come and mentor our new interns. It is a good thing. It is a good thing to give back, because the future of this project actually is a bigger one. As I discussed with Dr. Oki, as an agency, we are looking forward for the area of rocket to be grown into a full-scale industrial investment area. Bearing in mind that we are one of the first countries in the world to host a spaceport that is pre-independent, and you're all aware that we still host the San Marco Launch Center in Malindi, but due to other factors, it has laid idle, and the last launch took place in the 80s. So, as a country, we are looking forward to re-energize and reinvest in the area, looking at our ideal equatorial location and geographical suitability. So the agency is working with other government partners and international partners. We were looking forward to have the area revived, build another spaceport, Kenya, an equatorial spaceport in Kenya, and the plans are far ahead. We've done the basic preliminaries. Now we want to go into serious commercial feasibility studies, and hoping that in the next 3 to 5 years, we will have a place where we can practically apply our knowledge. And it will be this is a good foundation in terms of capacity building. And we look forward that these engineers won't just be doing this for marks. Please don't do it for marks. This is something that will be commercialized, and it will be for an advantage to our international community. So thank you, and please dedicate your time, knowing that it is about us, it is about the Kenyan space community, it's about the African space community, and it is about the global space community. So everything starts in this scale. This is a model scale, but it can be cascaded down into full scales. And if we realize the full scale, then you'll be able to say one day, I participated in a project that gave back to something great. Then additionally, as a parting shot, also this year we are organizing the Kenya Space Expo and Conference. So I'll urge you that we prepare what we will present to our space community, and every activity we've done, including the rocket that broke down, that's part of our history. As Nakuja, we will present what we've done. I hope you keep the archives of what you've been doing. Everything, including the Nakuja 1, Nakuja 2, the sample that we did, the samples that were launched and maybe failed. We will have that as part of our artifacts, because growth is a process. Somebody has to start from somewhere and head it somewhere. And those will be very precious gifts that will write our history in the near future. So let's all prepare for that. And I hope this time again we'll manage to secure a booth for you, so that we can showcase the progress that we are making in terms of rocketry. So thank you very much. And let's keep the spirit, and we'll be meeting more often this time round. Thank you, Dr. Okoki and the team.
Thank you very much, Captain Were, for encouraging us. And I also want to express our sincere gratitude to Kenya Space Agency. Without support from the KSA, we were not able to launch our N3 rocket. Thank you once again. And also, please, thank you very much for sparing your precious time with us, for guiding us, for instructing, advising us about the technical issues. And also for the Kenya Space Expo, we really looking forward to it. And if possible, we'd like to launch our rocket much earlier before the expo, let's say in April. And as you mentioned, maybe we don't need to carry 4, we can just carry 1 or 2 so that we can quickly test, which we believe it's surely work. So I think, yes, and also this is not just only the JQuad KU project, student project. So this is a collaboration, joint project with the KSA. And it is not only for technical exploration. This will aim the commercialization, industrialization. So this is a really a big project, and which is emerging. So I really want to communicate with the KSA. We want to include, we need you more frequently so that we can work more closely. Thank you very much. So I think Washington has been raising his hands. So could you make your comments?
Most of what I wanted to say has been said, but I just want to emphasize one thing, that we need to iteratively and continually test. I remember we got to a point last year when I had made a commitment that we're going to do a static test every day until we get the motor right. And so I'd encourage the team to just say the propulsion team specifically to build a very robust test stand, and then just find, say, a week or a few days to spare where we can run the tests continually. We did that to the extent that we could ideally predict what would happen to a motor even before we ignited it. And yeah, thank you.
Yeah, thank you very much, Washington. Anybody else? Any contribution from members? Okay, so if not today, I'm just going to create a document. So this is just a report for the launch. And pre-launch. So we have made a presentation. Some of us made a presentation, but from now on, we are going to compile what we have presented. And we are going to share with members so that we can, so everyone can refer to it, I mean, forever. And also this will be shared with KSA so that we can record our collaboration internally in Kenya Space Agency. And then also this is a report, rocket launch. And we need another document, which is manual, which has been advised by Ian. So manual for N3 rocket operation and assembly and preparation, work on site. Yes. So we are going to document for the future members and for the current members, how to prepare the launch, how to prepare the rocket, how to operate our rocket. So we are going to prepare 2 documents and share among the members. Then I just want to quickly go through. So we may not have much time for exhausting, but I want to request all the members visit this Excel sheet and fill in the necessary information. I have listed some of the information. For example, I think I have described, I have asked Paul and Harun to input the information. This is a measurement value. So even although the avionics system didn't work as expected, I think we have somehow recovered our apogee from the measurement manually. So for the first one, most likely the Tembo flew 93 meters. And because the flight duration was about 10 seconds for Tembo, Kabura 9 seconds, Simba 6 seconds. And I think most likely these rockets flew this kind of altitude. But again, our expected apogee was 1,600, which is way higher than this. So we have a lot to do to improve. And what I don't know is why the apogee recovered from the flight computer was not accurate enough. So I'm still analyzing it. So I think I'm going to discuss the recovery team again about why this has happened. And especially the logging data for the Tembo rocket, which has been recorded on the base station, seems to be working. So I think we can discuss this data. But still, we need to identify the issue of why the other logging data is. Oh, by the way, this should be Tembo. This should be Kifaru. No, this is Kabura. And this should be Kifaru or Simba. Simba. Yeah, so we may need to. So we need to analyze this data, and this analysis will be included in the report. Yeah, this one. Also, yeah, I think those are something I wanted to discuss in this meeting. Okay. Oh, as for the static test, which has been advised by Washington, I suggest if we are able, we want to do it this week because we have recovered, we have remaining 4 grains, which can be tested. So once the static test is okay and our ignition circuit is ready, I think we will be able to do the next test. And apparently we have to change the bolt. As I mentioned, it doesn't have enough strength. So as Nefat mentioned, we have to change it to the steel bolts. So I hope we can do it by Friday this week and ensure the motor will work properly. So yeah, so if we can confirm the static test, solid rocket motor operation, I think we are good to go. We will be able to launch our next rocket very soon, in the end of March or in April. And we are going to communicate with KSA for the next launch, the day of the launch. Okay, I think that's will be all for today. Anything, any other issues? Any other business?
I have a question.
Yes, please.
How come we didn't have a test launch this time? Or was it there?
Come again, test launch.
Yes, a test launch. Last time we had a test launch at JQuad. I remember I got to like 250 meters, then we went to Isiolo later.
Oh, good. Good point. As you, okay, this is a period regulation issue. So apparently it's the flight is regulated, less than 400 feet, like 120 meters. And as for the N2, my intention was kind of, we was, actually we were supposed to achieve only 100 meters. And so 210 was a kind of unintentional. It was a kind of accident. So ideally, we shouldn't have done any testing in JQuad because of higher altitude. And for the N3, apparently we are not able to do any launch or test launch. And what we can only do is the other testing, like a static test. And also, Dr. Mushiri, Dr. Patrick mentioned we should do a kind of a stress test. Like we are going to extract a part of the airframe, and we attach the rocket motor to the airframe and fire it, so that we can see if this our airframe material can withstand against the thrust generated from the SRM. So I think this is also important testing. And also any other testing, like drone testing to confirm the the state machine, and also ejection testing. Every testing, a unit test should be done on site, but this integration test can only be done in ECRO. Is it clear?
Yes, it is.
Okay, great. Thank you. And I have seen the Barbara typed on the chat box. She's saying, I'd like to suggest that the recovery team think of different stress tests for the flight computers and parameters for testing. Yes, that is true. So actually, the testing for recovery system, flight computer, is not sufficient. So we have to emulate the similar situation in their own site as much as possible. So we have never tested our system for more than 1 hour. So, and also we didn't shake our recovery system, avionics bay, too much. So, but we have to give the stress to our flight computer to see if there is any malfunction occurs. Okay, any other comments? By the way, you can always share your comments on the WhatsApp group so that we can incorporate your feedback. She's saying, Barbara's also saying the drone test is not the best for testing the state machine, in her opinion. So the team needs to think of something that simulate free fall. Okay. Yeah, so I think this was also raised by Mohammed or someone else, because yes, this is this graph. So the base station log for the Tembo seems to be working. However, the issue is the signal is lost at this point. So this point means after the apogee, so this is a free fall stage. So during the free fall stage, our signal was lost. So something has happened in the free fall. So we also have to simulate the free falls kind of situation. So that so ideally our system should work during the free fall. So, but we have to also come up with a kind of a way of testing the free fall situation. Thank you, Barbara. Any other contribution? If not, we will discuss as we will prepare this report and also the manuals. Okay, so thank you very much for your participation in the meeting. Thank you for your time. So now, although the rocket launch, the result was something we didn't expect, but we have been able to collect more data. And we actually it was a fruitful launch. I'm sure. So toward the next launch, we have a lot of material we can incorporate to improve our rocket. So thank you once again. Now we have a good momentum. Now the new interns are up and running. So let's work hard to achieve our milestone. So thank you very much for the meeting and have a nice evening.
Have a nice evening.